We went through this last time, all the key ideas here. And really the key terms are enantiomers, which are chiral molecules that can exist as a pair of what? Non-superimposable mirror images. When we assign R and S, we'll see that the R and S designations switch completely between two different pairs of enantiomers. If they're not enantiomers, if they're not mirror images, but they're something else, we call those diastereomers. Those are stereoisomers that are not mirror images. Okay, so there's two terms there you see. And then, yeah, R and S, we'll get to that. And specific rotation, optical rotation, we'll do that on Monday, I think. I'll point it out from time to time. That's the physical property. And again, the activity with biological molecules. So we pointed out that some drugs, their enantiomeric form can be a cure. The other enantiomeric form can be a toxin. Okay, so this is why it's a very important topic. And plus, most of the biological molecules that you'll see in biochemistry and in Chem 352 will be chiral. There'll be a lot of stereocenters. So we've got to keep track of this very detailed thing. So let's go over to the board here and see. So we wrote out, a bunch of molecules last time, and we'll start up here again with a bunch of examples here. And we're simply asking the question right now, is the molecule chiral or not? Okay. Does it have handedness or not? Okay. And what are the key things we need to ask about there? Let's see. Is it non-superimposable on its mirror image? Okay. Sorry if that's a little small there. If it's non-superimposable on its mirror image, we deduce that it is what? Chiral. Okay. Let's see if it lacks an internal mirror plane. Okay. It's chiral. Okay. If it has an internal mirror plane, some inherent symmetry, that means it's achiral. Okay. That means if we reflected it in a mirror, we'd be able to superimpose it on that object, and those are the same thing. It's just the same view of the molecule. Okay. And then stereocenters. Look for stereocenters. And here we're looking for carbons with 4 different ligands. And we'll circle those stereocenters, and those are the ones that are going to get the RS designations. And that will help us out keeping track of these things. Okay. So we're just inspecting these molecules, right? We left off with these two, which are actually trickier topics. Okay, this gets into the idea of diastereomers and meso compounds. But if we got cis 1,2-dimethyl cyclopentane, you see its mirror would look like this. Its mirror image, right? Those two methyls would still be up. And look, you could just take that object, put it right on top of there. These are the same thing. This molecule is therefore what? Achiral, right? So AC here. And you see the internal mirror plane. Okay. Now, if you've read ahead and paying attention, you actually see these are two stereocenters within the same molecule, but they're opposite of each other. One's R, one's S. Because of this internal mirror plane, look, it's achiral. So we go to all this trouble of doing R and S, and then we throw that fly in the ointment, right? Oh, by the way, it can still be achiral if it has this mirror plane. And that's where all the stereocenters, there has to be symmetry. Both sides are the same structurally. And the two stereocenters here are opposite of each other. Okay. That'll become more apparent. Here, let's see if they're trans to each other. What would this guy's mirror look like? Mirror image? It would look like this. This one up over here, reflecting right there. And this one, what, down, reflecting right there. Now, if you take this and put it on top of this, look. They're not superimposable. The two methyls are out there, okay? That's because they're both of the R stereocenter. This is the RR, and this one's the SS, okay? So this one is not superimposable on its mirror, so therefore it's what? It's chiral. Sorry, I need a C there, right? Okay. All right, now if you struggle with that one, don't worry. We'll assign R and S, and hopefully that'll make more sense here in a second. Let's go up to some simpler ones here now. What about this 2-fluoro compound here, chiral or achiral? Now don't just look for the dash or the wedge there. Oftentimes we draw things with a dash or wedge. That just implies, the geometry, whether that group's going into the board or out of the board. And that's tetrahedral carbon, right? So here I'm not drawing it. But does this carbon right here have 4 different ligands on it? Yeah, most people know. So let's circle it. That's a stereocenter. So get in the habit of circling the stereocenters. There's 4 different groups. Don't forget about the hydrogen there. And the methyl here and the propyl on this side, those are different, okay? We'll go down and break the tie there. Don't say that, oh, this is a methyl, that's carbon, and this methylene, that's carbon too. Those two are the same. So it's really only 3 different groups. No, that's a different carbon than that carbon. Okay, so there's 4 different groups here. This is indeed chiral. We may draw this with a solid wedge or a dash wedge. That'll imply which enantiomer we have. But this molecule itself right here is chiral. Okay, it can exist as a pair of enantiomers. How about this one? How about if we move it over to the 3 position? Chiral or achiral? Somebody's nodding their head. Can you tell us why? A couple things. Somebody said, well, there's a line of symmetry here. You can see that mirror plane right through the molecule. This ethyl and this ethyl reflect each other internally. And plus, is that a stereocenter? You mentioned that too, right? The 2 ethyls, yeah, are the same. So there's only 3 different groups. There's got to be 4 different groups to be a stereocenter. So what? Achiral. Very good. How about isopropyl alcohol? Chiral or achiral? Let's see if we're getting a little better at this. Can somebody tell us? Achiral. Very good. Why? Yep, they're saying 2 methyl groups on the side, so internal symmetry again, not a stereocenter. We're not circling that like we did with the 2-fluoro. How about this? Cyclohexene all. And I'm drawing a solid wedge for you here. So can you identify a stereocenter? And if you can, is the molecule then chiral or achiral? Is there a stereocenter here? Yeah, everybody's nodding. I'd want to circle right there, okay? Don't forget about the hydrogens in the back. We often don't draw that in there. We'll see pretty soon that that's the R enantiomer. Okay, it can exist as a pair. The S, we just invert that. But don't worry about this alkene. That means this carbon here is different than this one over here. And there's no internal symmetry to this. This is different than this molecule, right? What if we drew this? Oh, look, I've drawn a dash wedge there. It must be a chiral molecule. No, cyclohexanol with no alkene here. Is this chiral or achiral though? Achiral. Why? That's not a stereocenter and it has the mirror plane. Okay. This one though is definitely chiral. Okay. That makes sense so far? Okay. These simpler ones, if one stereocenter is present, it's always chiral. Okay. It's when you get 2 or more that things can get a little crazy. And that's with this guy here, right? We have to examine it there. Question on this? Okay. So this is R. Yeah, very good. We'll get to that in a second. Let's do a few more examples here. How about this one? Trans, 1,3-dimethyl cyclohexane. Chiral or achiral? Does it have internal mirror plane symmetry? No. Okay, because they're trans to each other. Are there stereocenters here? Does this carbon have 4 different groups? Well, you could say, well, there's methylene, methylene. But then look, you get to methylene here and methine here. So you keep going down the chain until you break the tie. The point of first difference, we'll see that assigning R and S. But for the symmetry, there's no plane right here because this one's down, this one's up. Okay? So that is indeed a stereocenter, and so is that. So what do we determine here? It is indeed what? Chiral. Okay? And we'll assign stereocenter. I think this is the RR enantiomer, okay? It has an SS partner, okay? That's not shown here. Its mirror image would be the SS, by the way. Okay. What about this one? We're simply moving the methyl over. This is trans, 1,4-dimethyl cyclohexane. Chiral or achiral? Apply the criteria here. Are there stereocenters? Is this a stereocenter now? No, because methylene, methylene, methine. Look, methylene, methylene, methine, and then all the way around. That's not a stereocenter now because it's 1,4. Okay. Got to inspect it, right? This one also not a stereocenter. And plus, what else do you see here? An internal mirror plane. Okay, right through that portion of the molecule. You didn't have it here because this was just a trans air, and we couldn't put the mirror here, right? Because that has the methylene and 3 methylenes over here. That's not a plane right there, okay? But this certainly is, okay? So even if this is cis or trans, if they're 1,4 symmetric that way, achiral. This one was chiral. Okay. Epoxides. These are the tricky ones. These little cyclic ethers. Assigning R and S will be tricky. The easy part is assigning whether they're chiral or not. And that's what we look for a stereocenter. Look for a carbon with 4 different groups on. And by the way, this implies a stereocenter always has to be what hybridization? Always sp3. Okay. That's the only way you can get 4 groups on a carbon. If it's sp2 hybridized, it's got an alkene or a double bond to something, right? An sp, triple bond. It's got to have the 4 because that arrays it in 3-dimensional space that lets us talk about this relationship, okay? Being non-superimposable. By the way, we can review that real quick. So here's our model. Let me see if I can get back to it. So there's a typical molecule with 1 stereocenter, okay? Just 4 different groups on it, and these are indeed enantiomers. You can see the relationship there. And are they superimposable? Well, we can get the black with the yellow, but look, the purple and the red, and that's hard to see on the camera. Purple and red can get together, but look, black and yellow are not congruent. They're not superimposable. So do this trick, okay? And if we invert the stereocenter exchange in E2, then we'll get the same molecule. It will be congruent, okay? But this issue of having a stereocenter means what? That we've got this relationship, this strange property of carbon. It's a rather simple object, right? Tetrahedral carbon, but with 4 different groups on it, we have this idea of symmetry, and we've got to worry about this pair of enantiomers, okay? Kind of weird, but yeah. So here it is here. Is that a stereocenter in this epoxide, that methyl? No, there's 3 hydrogens there. Is that a stereocenter? Yeah, okay. People are nodding. Why? Because there's a methyl, a methylene, an oxygen, and a hydrogen here. So circle that, stereocenter, okay? That can exist to a pair of enantiomers. How about this? Is that a stereocenter? No, it's a methylene. It has 2 hydrogens, okay? So a total of 3 different groups. Not a stereocenter. How about that? Dimethyl epoxide. Stereocenter, is it chiral? No, these 2 are the same, okay? And then 1, 2, second different group, third different group. So that's not a stereocenter. So this one is chiral. This one we deduce as being what? Achiral, okay? And you'd see there'd be a mere plane right through here that would reflect everything on the other side. Okay, so that's achiral. Let's do a couple more of these and let's get into RNS real quick. So a little bit more complicated. How about a couple drugs here? Ephedrine, got an amine, a methyl group. Oh, how about ketamine? That's a pretty potent drug. Got a benzene with a chloride. And here we got to deduce whether it's chiral or achiral, and where are the stereocenters? How about a couple chlorides? Oh, vinyl chloride. Dichloride. Oh, and another vinyl chloride. Oh, I'm drawing a dash. Chiral, achiral. And circle stereocenters. See if you can do that. Okay. How about this first one here? Chiral or achiral? Oh, that's kind of messy looking. That amine, there's a nitrogen on there with a hydrogen. Yeah, okay, it's a methylamine. Okay. Chiral or achiral here? Who can tell us? Yes. 2 stereocenters, where are they? Okay. Yeah, there's no internal mirror plane, so we don't need to worry about it being a meso compound. We'll get to that in a second. Meso compounds are the weird ones where there are stereocenters, but because of the internal mirror plane or center of symmetry, they become achiral. Okay? But this one's definitely chiral. There's different forms of this. In fact, with 2 stereocenters here, we can have it either up or down. Those are the 2 different positions we can have, R or S. And then depending on how many stereocenters we have, N gives us the total number of possible stereoisomers. And this is kind of bad because here we've got 2 stereocenters, so 2 to the 2 power, that's 4 total isomers we can have there. Now let's look at a molecule real quick like cholesterol. which we've seen before. You can't see the detail there, but you can count up all the stereocenters. That's actually 8 stereocenters in cholesterol. Nature just makes the one enantiomeric form. It is a chiral molecule. But because there's 8 stereocenters here, mainly at the ring fusion positions. Remember, it's a bunch of fused cyclohexanes and then a chain here. The chain has 1 stereocenter too. You can come up and look at this afterwards or go back to the book and examine the structure. But we've got 8 stereocenters in cholesterol, so that's 2 to the 8th power. So how many possible stereoisomers are there for cholesterol? Ouch. Do the math real quick. What is it? 256. Yeah, ouch. You wouldn't be laughing about that on a test if we told you draw all 256 isomers out. No, we're not going to have you do that. But you can appreciate that, right? Mother Nature makes the one form. And that's because there's chiral enzymes, catalysts that control the biosynthesis of cholesterol. It just makes the one enantiomeric form, which I think is an amazing thing. And you'll appreciate that a little more as the course goes along. Let's get back to this. So ketamine, is that a chiral molecule? Where's the stereocenter? It's right here, right? There's no hydrogen there, but those are 4 different groups, the carbonyl, the methylene, the aromatic. There's no stereocenter in the aromatic. Why? Because it's sp2 hybridized carbon. You don't need to worry about that. Look for the sp3 ones where there's 4 different ligands. Certainly there's 4 there, so chiral, okay? It's just 1 stereocenter, so it's just 2 enantiomeric forms, okay? 2 to the 1 power, okay? And then this strange looking guy, got a double bond here, a methine here, a methylene with another chloride. Chiral molecule or achiral? What do you say? Chiral. And where's the stereocenter? Right there, okay? Can exist in 2 forms. How about this one? We've got another vinyl chloride. No stereocenters here. That's sp2. How about that methine? Oh, is that a stereocenter? No. Very good. A lot of people shaking their heads no. Why? Because the 2 methyls are the same. So not a stereocenter. We'd say achiral. Okay? That would be superimposable on this mirror image. Don't be tricked out by me drawing this dash back here. That's just one conformation. We can rotate all we want around there. But because that's not a stereocenter, this is an achiral molecule. Okay, you okay with that? Okay. Yeah. How to draw the enantiomers. Okay, this is a good thing to review too. We did a little bit about this last time. If we've got a chiral molecule, and we can deduce that indeed it is chiral, okay? This alcohol with that solid wedge coming up, there's 2 ways to draw the enantiomer. And the enantiomer, remember, is the mirror image, okay? We'll see in a second it's the R or the S form that's inverted there. So let's invert this stereocenter. We can do it a couple ways. We can redraw the chain and everything just the same and just invert that. And by invert, what do we mean? We exchange the hydrogen and the hydroxyl. Okay, and I did that with the models last time. That now is the mirror image form. Well, wait a minute. Remember last time we made a deal with the mirror here and we looked in the mirror? What would that image look like? It would look like this. Okay. Wait a minute. That stereocenter is still coming out at you, right? But wait a minute. Is this the same as that? Yeah. Just flop this around and you see these are the same. These are just 2 different ways of doing it. Here is the mirror image, right? And here it's just inverting all the stereocenters. We arrive at the same compound. It's just 2 different ways of doing it. Whatever way is more convenient. Sometimes it's more convenient just to invert all the stereocenters. Okay. Remember, you have to do all of them to get to the enantiomeric form. And what do enantiomers mean? They're stereoisomers that are not superimposable. So if we took this here and tried to impose it here, the hydroxyls and the hydrogens would not be congruent with each other. Okay. Very good. Let's get into this RNS deal here. Oh, there's one more I wanted to show you. A molecule can be also achiral if it has what's called a center of symmetry. And this is another kind of strange thing. But if you have this type of molecule here, let's see. And we'll see it with meso compounds too coming up in a second here. this idea of the symmetry. But if you make a model of that compound, well, if you first look at it and try to assign R and S to each one, which we'll get to, you see there's no actually mirror plane symmetry here. But right in the middle of this molecule, every atom reflects right through that center. And if you have this internal, what's called a center of symmetry, that's just like having mirror plane symmetry in a molecule, and it makes it what? Achiral. So don't worry about that. I think there's just a couple examples doing that in the book, and yeah, we won't worry about that. All right, let's go back here to our pair of enantiomers we've been talking about, and let's assign R and S here. So we've got a process here. These two compounds have the same melting point, boiling point, and spectral properties, NMR, IR, everything except optical rotation and how they interact with other chiral molecules, including chiral receptors. And we'll need to look at that later. But let's do a designation here of R and S. So these are the Coningal Prelog SIP rules, part of the IUPAC convention. And what you do first is ID your stereocenter. And that stereocenter is what we're going to be assigning R and S to. So let's identify our stereocenter, okay? And we're going to have to prioritize now. Prioritize what? The 4 ligands that are on that stereocenter. So what do we have? And we should draw our hydrogen in there, okay? And prioritize, what do we mean? We're going to have position in the periodic table, and it's a point of first difference. So if it's a carbon-carbon comparison, keep going down the chain until you can break the tie. Or if it's all the same, then it's probably not a stereocenter, okay? So this should tie into what we've been talking about here. And periodic table, what do we mean there? Okay, so top priority here, oxygen, carbon, carbon, or hydrogen. And it's prioritized the 4 ligands on the stereocenter, directly attached to that carbon that is the stereocenter. Okay, that's kind of the key. So what would we prioritize here? Oxygen would be number 1. Okay. Let's see, carbon, carbon, or over hydrogen. Hydrogen would be the 4th. Okay. And we're just prioritizing the ones on that stereocenter we circled. How do we do this one? Methylene versus methyl. Well, a methylene is CH2 with another carbon, right? A methyl CH3. So which one has higher priority? The methylene, right? So this would be 2, and then 3, and then 4, the hydrogen in the back there. If we have isotopes, tritium over deuterium over hydrogen, these are the heavy isotopes of hydrogen. So in the periodic table, you know, these are the same. These are isotopes of hydrogen. But more what? More neutrons here. 1 more neutron, 2 more neutrons for tritium. And that comes up sometimes. Okay, those are different ligands there. So we prioritize here. And now the next step, and this is kind of a key here, put number 4 in the back. Okay? And number 4, rotate from 1 to 2 to 3. And if that rotation with number 4 in the back is what? Clockwise, that is what designation? R or S? That we will call R. If that rotation 1 to 2 to 3 is counterclockwise, we designate it as S. Okay. Where'd they come up with this R and S thing? Believe it or not, it stands for the Latin rectus and sinister. And it comes out of some old thinking. Right-handed people are the righteous or the rectus people, and left-handed people are the sinister or the evil people. How many lefties do we have out there? What are we doing about proudly admitting it? There you go. Okay. Yeah. So this rotation. So there's some directionality here we need to talk about. So let's see. Let's hold this with our hand. There's my hand in the back. Okay. I'm holding number 4, and I'm rotating 1, 2, 3 there to do this form of butanol. So is this the R or the S enantiomer? Am I rotating counterclockwise or clockwise? So let's see. Let's have, here's the hydrogen in the back. My hand's holding it. And here's purple, oxygen, ethyl, and then methyl. So I'm looking right down this front atom. Okay. And I'm rotating from 1 to 2 to 3. Am I rotating in a clockwise or counterclockwise direction? Counterclockwise. So is this R or S? Come on, be brave. It's therefore what? S, right? That's the S form, okay? Now let's do this one over here. And we what? Inverted that stereocenter. And, you know, now we've got the hydrogen in the front, but that's okay. We can just take that hydrogen that's in the front, right? Rotate it around, and now we're rotating what? From 1 priority, 2 priority, 3. And you can kind of do this just with your hand if you have it in the back. Or you notice that this hydrogen is in the front, and just do the rotation 1, 2, 3, and that's counterclockwise again with this in the front. But if you look at it from the back, that's what? That's going to be clockwise. So this is what? That's R. And you can flip the whole thing around, right? And if you flip it around, you'll have this, what, in the, well, let's do this carefully here. So if you pull this around, right, you'll have what? You have the ethyl back here, and now you have the methyl in the front. Okay, that should be the same as that. I just flipped that around, what, 180 degrees. And so now we have what? 1 priority, 2, 3, 1, 2, 3. And our hydrogen's in the back. And hold that with your hand in your mind's eye, whatever. 1, 2, 3. And that's what? You see it's clockwise. So what? That's still R. Okay. These are the same molecules. This is the mirror image, the S form. Okay. So let's do some more of these examples and see what else we can do here. How about this one? Let's do the one that we had up before. How about this? Alcohol and the alkene. Now we said that was chiral, and I'm drawing the thing there. RS, so put the hydrogen in the back, that's 4. Oxygen's still 1. What breaks the tie here? Methylene or carbon doubly bonded to carbon. If you doubly bonded, you count it twice, okay? So this is bonded to what? 2 hydrogens and a carbon, okay? That one to break the tie. This one's bonded to what? 2 carbons and a hydrogen. So what gets number 2 priority? The alkene or the methylene? The alkene, right? So this would be 2, 3. So 1, 2, 3. Again, we got to hold that hydrogen in the back. So is that counterclockwise or clockwise? That's indeed clockwise. So that's your R. Okay? And we could draw the S just by inverting that. Okay? You'd soon be rotating the other way. How about this one? We're kind of going through a progression here of different functional groups. So where's the stereocenter? I put 2 fluorides on there, so that carbon bearing the fluorides is not a stereocenter. Our alcohol is still a stereocenter, right? What about priority? Well, 4, 1's still here, right? Because that's what's directly attached to carbon. This is a carbon on this carbon. Okay, so that breaks the tie first. Some people look at these fluorides and say, well, fluoride's further on in the periodic table than oxygen, so why isn't that the top priority? Well, because the carbon's directly attached here, okay? So this is 2, and then the methylene here is 3. So again, that's what? An enantiomer? That is the R still, okay? Everybody see that, okay? Well, how about this, where we don't even have a hydrogen We've got a fluoride and a methyl. You don't have to have a hydrogen. You have to have 4 different ligands. You put the lowest priority one in the back. Oftentimes it's hydrogen, okay? But in this case, it's actually going to be what? Not the methyl, right? CH3. So circle your stereocenter. That's always good form. Identify the 4 ligands. So they're there, and there. What's your top priority one now? Now you use the fluoride. That'd be number 1, okay? And then you got carbons, right? You got a methyl, a methylene, and a carbonyl. Which one's next? Which one's 2 priority? Carbonyl, yep. Which one's next? Methylene, methyl, the methylene, because that has a carbon on it. And then the methyl's last. Oh, so it's a little trickier. You got to hold this one with your hand. That's number 4. That one always has to be in the back, right? Put it in the back. Number 4 has to go in the back. If you don't have it in the back, you're going to mix it up. You're going to have just the opposite thing here. So hold that number 4 and then rotate 1, 2, 3. That's what I'm doing, right? And you can pull this out. Is that counterclockwise? Yes, it is. So this is S. Okay, so it's a little bit tricky there to keep that straight. Let's do a epoxide one. We got a benzene on there. Chiral molecule or not chiral? That's the first thing you ask. Then is the stereocenter there? Yes, there is. Where's the stereocenter? Right here. Okay. Add in the hydrogen. We're giving you some bold geometry there, so it's coming out at you. Now assign priority on the stereocenter. What's the top priority group? Oxygen. Very good. Hydrogen will be 4. That's obviously the easy one, unless there's an isotope. It might be deuterium or tritium. And then what? We've got 2 carbons here. Carbon, carbon, carbon that this guy's bonded to. And what's this one bonded to? Oxygen, hydrogen, hydrogen, right? What is this carbon bonded to? Oxygen to hydrogen. What breaks the tie? What's the first thing? Periodic table, right? So even though this carbon here of the benzene ring has 3 carbons on it, we count twice here. This one has what? An oxygen on it. That's why epoxides are tricky. It goes back in the ring, right? So this has an oxygen and then the 2 hydrogens on it. So that's number 2, I think. This is 3. So 1, 2, 3. Looking down right the front of that. With that one in the back, there's your hand, there's your eye. Okay. Then your hand's going to do the clockwise or the counterclockwise. And so what is this? 1, 2, 3. Is that rotation clockwise or counterclockwise? It's clockwise, right? So this is indeed R. Okay. Questions on that? All right. Very good. Let's boldly go on here to diastereomers. Just when you think you have this all figured out, we give you another challenge. 2 stereocenters or more. Okay. 2 or more stereocenters. So if we got 2 here, we could have the RR form. Okay. So if we do our designation, the enantiomeric form would look like what? It'd be the SS. Okay. And that's what we'll look for. We'll assign R and S to each stereocenter. We've got a molecule. We can have 8 stereocenters like cholesterol. We can figure it out. We're not going to ask you to keep track of 256, but you could actually. Okay. Here we'll do simpler ones, right? If it's RR in one enantiomeric form, the enantiomer of it, the non-superimposable mirror image, will be SS. What about this? What if we just change one stereocenter? What's this relationship now? These are stereoisomers that are not mirror images. And so they're what? Not mirror images. So we call them what? Not enantiomers. We call these enantiomers, RR and SS. But the RR and the SR What do we call those? That's that other crazy term, right? Starts with a D. What is it again? Diastereomer, right? And that's, yet another term. It's diastereomeric to its symmetry relationship. And that means it has one or more stereocenters off. If it has all the stereocenters inverted, it's enantiomeric. If it's one or more, but not all of them, then it's a diastereomeric relationship. They can have different properties, melting points, different spectra, different reactivity. Diastereomers are very different stereoisomers, even though it's the same constitutional isomer, right? But the stereocenters are arrayed differently, okay? And that leads to the difference. So let's do an example here. Here we got a carboxylic acid with what? 2 alcohols. How many stereocenters do we have here? Dihydroxybutanoic acid. How many stereocenters? 2. So how many possible stereoisomeric compounds can we have in this series? 4. And that's that 2 to the n power rule. 2 stereocenters, and those can be 2 different orientations, right? R or S. So 2 to that 2 power, because there's 2 of them, means 4. Let's see if we can draw them out. We've got the RR, and we'll verify that this is R and R. Okay. Let's see. So here we got the bold thing, hydrogen in the back. We won't do them all, but we'll do a couple of them. Top priority, oxygen, stereocenter. We do them one at a time, right? 2 of them. Top priority, the next one is carbon-carbon. This carbon has 3 oxygens on it. This carbon just has 1 oxygen. So this is the next priority, carboxylic acid. And then the third priority is there, 4th is that. So is this indeed R? Yep, clockwise, right? And I think you can do this one too. There, I did it really fast for you. Does that make sense? Is that clear now? Go back through it slowly and verify that that one's indeed also R. Okay. So let's see, what would we do to draw the SS? We'd invert both stereocenters. Is that indeed the SS now? The enantiomer. We inverted all the stereocenters. Yep. And so let's verify this one. Let's verify that one right now. So it's top priority, second priority, third, and then the hydrogen's in the back. Counterclockwise? Yeah, sure is. Okay. S and S. Okay. Now, here's the crazy thing, right? The SR. So, which one are we going to change and which one are we going to keep the same? And let's verify that, they wouldn't be mirror images now. Let's keep this R the same right here. Well, let's invert that one to S. Oh, we already got it right there. So we can already verify that that's S. Okay. Oh, look, they're both coming out. That's the SS, or the SR form of this molecule. Its relationship here is diastereomeric. The relationship across here, what did we say, was enantiomeric. Okay. And now let's see. Let's do the enantiomer of this guy. Will that give us the 4th one? And remember, to do an enantiomer, we need to do what to the stereocenters? Invert 1, but not all, or invert all? Invert all. Okay, that's the vote here. Let's invert all of them. And I think you can see, that one would have to be down now, and this one would have to be down also. And is that a distinct one? We haven't drawn this one where they're both down yet, have we? And that should be what? The RS. Okay? And so let's verify here. Yeah, indeed, these are enantiomeric, SR to RS, inverting all the stereocenters. And then here, what's the relationship here between SS and RS? That's, again, diastereomeric. Yes, question? Well, you look at each stereocenter individually. Okay? So these are both RR. Okay? This one's still R. This one's still S. Yeah, you inspect each one individually. So the question is, how do you tell which one's SR or RS? And my answer is inspect each stereocenter and keep track of them individually. And then it's a relationship between the two. If you have SR here, this better be what? RS. And you can verify that by looking at that. Yeah, another question, please.
Do you just arbitrarily assign one to be the first part and one to be the
Sure. I started with RR. I could have started with SS or RS. It's the relationship and the absolute stereochemistry, R or S, that's important. But you have a way of figuring that out, right? Following the route there. There's a couple other relationships to talk about here, these cross relationships. What's the relationship between RR and RS? Diastereomeric. Yeah. What's the relationship between SR and SS? Also diastereomeric. So what do you notice? Within the series, there's a lot more diastereomeric relationships. And same thing with cholesterol. If we drew all 256 out, there'd be a ton of diastereomeric relationships. But there would be these enantiomeric relationships where all the stereocenters are opposite of each other. Okay? So yeah, I agree. There's a couple different ways to do it, but keep track of it sequentially, and then the relationship is really the important thing, depending on which one I started with. Does that make sense? We'll do some more examples here. We got some more time. Let's do another one. And I like this one. In fact, let's do a couple. We've got time here. How about this series? This is coming out at you. So bromochloro here. This is the RR one. So see if you can draw the other three, right? And however you want to keep track of it. And then let's do this one. Dibromo Butane. And we'll start out with the RR. We could have started out with other ones. That's just where I started here. So we got RR here. Let's draw the mirror image. And I like, either inverting the stereocenters or drawing the mirror image. So if we do Lewis Carroll, go with Alice through the looking glass. Anybody read those books? Nobody in the last section read the Bizarro World. Okay, whatever. Okay, so this one would be chloro up, bromo down. And again, this is coming out at you here. So yeah, how is this R here? Well, top priority would be chloride. And again, we're just looking at that stereocenter, right? 2, 3. Got to put our eyeball back here, right? 1, 2, 3. So is that R? Yeah, it sure is. Okay, R right there. So if we do the inverted thing, this will be the SS. Okay. Here, let's do just one at a time. Let's keep chloride the same. So that's R over here. And then bromide's also up, so that's the S right there. Okay. I'm going a little fast here. This relationship, it's enantiomers. This relationship, RR to SR, is indeed what? Diastereomers. Let's do the enantiomeric relationship here, where they're both up, but the stereocenters are inverted. This is indeed the RS, okay? Enantiomers, okay? And then all the others are diastereomers. The cross relationships and that. 2 stereocenters, cyclopropane, a little harder to see, but I think you can assign R and S. Make models. That's another answer to the question here. How do you figure this out? If you physically make a model, then you can hold the fourth one in the back and rotate, clockwise, that's R. If you're rotating counterclockwise, that's S. And you need to do that. If this is still fuzzy, make sure you go through that. Let's finish up with this one. So RR, and let's just invert both of them. Could draw the mirror image where it'd be flipped around a little bit. We inverted both here, so that's indeed the SS. Okay. Let's just invert one here. So R. Sorry, we need BR there, don't we? R. Okay. But if this one's the same, that's the RS. Okay. And what would the other one here be? That'd be the SR. But now there's something a little bit fuzzy here. Who can tell us what might be a problem here? Are these really diastereomers of each other? Or enantiomers, I mean? Okay. Enantiomers up here at the top. That's true. RR to SS. Relationship here, but question mark by the enantiomer there. Somebody have a problem with that? Somebody who might have read ahead? What do you see? These two ends are the same here, right? And the two groups are the same. What if we rotate around here and look at a different conformer of that? If we rotate around this bond, look, it puts that bromide up right there. What do you notice about that geometry right now? You can draw a mere plane in that molecule. It does have two stereocenters, but what? It's got planar symmetry. And notice the two stereocenters, R and S, are reflections of each other through that plane. In fact, there's a center of symmetry right here in this orientation of that molecule because one's up, one's down. And there's symmetry. The two ends are the same. So what? We have a center of symmetry here and a mere plane with this conformer. So therefore, this molecule right here, is it chiral? No. And it was pointed out here, this molecule is achiral. And this right here is indeed its mirror image, but you could take this and rotate and flop it right on there. It'd be congruent. It would be superimposable on its mirror image. So therefore, it's what? Achiral. But because it has stereocenters, let's circle them. They are there. We have a special term for this. It starts with an M. Meso. Okay. Meso are achiral molecules that have stereocenters. So you have to be careful here. Even though there's two stereocenters, that's a possibility of 4 total isomers. But there's really only 1, 2, 3. These are the same. Okay? So if there's a mirror plane or symmetry relationship, and you look at it, if the ends are the same and all the stereocenter groups are the same, and the stereocenters are reflections through that center, then it's achiral. That's the trickiest part, and we'll review that next time, and we'll do optical rotations and everything else. Quick question. Sorry, I went a little bit over. Should be okay. All right, work the problem.